This episode is brought to you by Brilliant. In 2022, over 2.3 million tons of synthetic foam was produced globally. By volume, this is roughly 76 million cubic meters, or about the volumetric equivalent of 29 Great Pyramids of Giza. Foam is a key component in a broad range of manufacturing processes. It can be found in furniture, thermal insulation, acoustic products, impact protection components, seating, and packaging materials, as well as numerous other mass-produced products that we frequently use. And like many of the common materials we use daily, the story of foam is far more complex than it seems. Evolving from a century of research that iteratively enhanced its physical properties, this natural phenomenon has become a critical material to the modern industrial world. Foams are a type of material known as dispersed media. These materials consist of a dispersed phase substance that is distributed in another continuous phase substance. This concept is commonly encountered in colloids, where fine particles are dispersed in a film medium, such as droplets of oil in a water-based emulsion, and solid particles in a fluid suspension. In a foam, gas bubbles are the dispersed phase substance, and they are trapped within the continuous phase of either a liquid or solid substance, giving foam its unique structure and characteristics. In most foams, the volume of the dispersed gas is far larger than the liquid or solid material separating the regions of gas. Foam formation is a common process in nature. Sea foam, for example, forms from the organic breakdown in oceans and wave agitation. Tree sap can also foam in certain species as a response to bark damage. Whipped egg whites in meringues represent culinary foams, while the froth in fermented drinks like beer arises from carbon dioxide release during fermentation. Soapsud formation from the trapping of air by agitation in surface tension reduced water is also another common foaming action. To form a foam, three conditions are essential: mechanical action, surfactants to lower surface tension, and rapid foam generation compared to its rate of breakdown. Essentially, work is required to expand the surface area. Foams are considered multiscale systems as they possess various levels of structural hierarchy spanning from the molecular to the macroscopic scale. This scale begins with the individual surfactant molecules that form the stabilized gas pockets and pans backwards up to the interconnected network of cells that form the bulk foam. At the intermediate level of the scale is where the equilibrium of the continuous film creates a foam's structure. In this structure, where the liquid film junctions with three or more other bubbles are called plateau borders, while the face of the film between two bubbles is known as lamellae. When four plateau borders meet, a vertex is formed. Foam bubble shapes depend on the relative volume of liquid and gas they contain. Typically, the gas volume in foam ranges from 50% to 95% by proportion. Foam films tend to minimize their surface area given a boundary, leading to a spherical shape with lower proportions of gas. When this volume exceeds 75%, the bubbles begin to deform each other. As liquid drains, bubbles merge and the foam takes on a polyhedral shape at the edges. This polyhedral form arises from fluid moving from the bubble walls to the vertex, driven by pressure differences caused by the curvature of the bubbles. A foam bubble's stability is determined by two counteracting forces acting upon it: its film surface tension and the excess pressure or the pressure difference between inside the bubble and outside the bubble. Surface tension drives to minimize the surface area of the bubble, however, the excess pressure counteracts it and equilibrium bubble size is reached. The stability of foam depends on multiple components that affect its film surface energy. Film elasticity is an example of a key property that is the result of this dynamic. Film elasticity creates a self-repairing behavior known as the Marangoni effect that contributes to bubble stability. In soapy water, for example, the surfactants or molecules that have water-attracted and water-repelling ends position themselves based on their attraction to water. If a force thins a part of the bubble walls, it increases both its surface area and tension. This change reduces the surfactant concentration at that spot. To balance this, the surfactants move towards the thinned area, dragging with them some liquid. This movement effectively repairs the weakened spot. For a liquid to foam, it needs surfactants. pure liquids will not foam. The amount of solute in a solution influences its ability to stabilize a foam. At low concentrations, there's minimal impact on foam stability. However, at very high concentrations, the foam might destabilize due to overly fast diffusion. Optimal elasticity is reached just before the critical micelle concentration. Beyond this point, adding more surfactants does not affect the foam's elasticity, but leads to more micelle formation or clusters of surfactant molecules within the solution. An ionic surfactant will add stability to the film because of the repulsion of the two film's surfaces as they thin. However, these van der Waals forces only contribute to foam stability only at thicknesses of 200 nanometers or less. The presence of absorbed surfactants at the surface interfaces can also increase intermolecular forces within the foam bulk by making the surface layer more viscous and rigid. A practical example of this effect is cappuccino froth, in which milk proteins stabilize the foam, ensuring it lasts after steaming. Milk contains water, fat globules, and proteins. When heated, these proteins break and the molecules unravel, reinforcing the bubble walls and stabilizing the foam. The increased viscosity slows down drainage and collapse, though if the viscosity becomes too high, the self-healing surface transport mechanism diminishes as the foam becomes more rigid. In a forming foam, bubbles with smaller radii have higher internal pressures. As the bubbles merge, larger bubbles grow by absorbing smaller ones because of this pressure difference. Gas from high-pressure bubbles tend to move to these bubbles with lower pressure. When surfactants are present, they pack closely to the bubble walls, reducing this gas movement. Typically, lighter surfactants are more effective at this because they can pack more tightly onto the surface. Preventing foaming is also a highly desired property in many processes. Anti-foaming agents attempt to create failure points in the foam stabilization mechanism in order to accomplish this. The common rupture mechanisms to collapse foams are spreading and lens formation. In spreading, a disruption to the film surface tension gradients is created, forming a region with low surface tension. The anti-foam agent produces this area, and instead of self-healing, the changed tension pulls fluid away, thinning and eventually breaking the bubble. In lens formation, the anti-foam agent creates a lens between interfaces. Due to capillary pressure, fluid flows from the anti-foam area to a lower pressure region. Over time, the film will sufficiently thin and form a hole, causing the bubble to rupture. A foam in which the continuous phase medium becomes rigid through various stiffening processes is known as a solid foam. These foams are typically classified into two types based on their pore structure: open-celled structured foams, or reticulated foam, and closed-celled foams. Open-cell foams have interconnected pores, resulting in a softer texture. These foams can absorb any surrounding gases. In contrast, closed-cell foams possess isolated pores, contributing to their greater compressive strength. They're typically denser and more costly due to their composition. These foams can be enhanced with specific gases for superior insulation. They stand out for their robust dimensional stability, minimal moisture uptake, and greater strength than their open-cell counterparts. When viewed from a macroscopic level, solid foams can be treated as a continuous material that are referred to as cellular solids with predictable mechanical properties. The mechanical qualities of foam are gauged using compressive stress-strain curves. Initially, when foam is compressed, it responds elastically due to the bending of its cell walls. Following this, as these walls buckle, the material weakens and starts to give away. Ultimately, when cell walls press against each other too intensely, the foam breaks. From early in human history, natural cellular solids such as cork, wood, bone, and sponges have been an integral part of tool and structure construction. However, it would not be until the late 1800s for manufactured foam to come into use. The first manufactured foam products were created from natural rubber latex and were a direct result of the process of vulcanization. Pioneered by Charles Goodyear in 1839, vulcanization revolutionized rubber's properties, making it more durable and elastic. This laid the groundwork for the development of various rubber products, including foams. Foam latex is made by blending a liquid latex base with additives, whipping it to introduce air, and then setting it in a mold to vulcanize and solidify. The main ingredients include the latex base, a foaming agent for frothiness, a gelling agent to thicken it, and a curing agent to ensure it vulcanizes and hardens when baked. Depending on the final use, other special ingredients might be added. Known as the DUNLOP process, this method for creating foam latex created a continuous, uniform batch in a staged operation that was inexpensive and efficient. While natural latex foams had many commercial possibilities such as energy absorption and thermal and acoustic insulation, it would not be until the late 1920s for synthetic blended variants of the product to begin to grow in popularity, particularly for film makeup and prosthetic use. The mid-1850s also saw the discovery of urethanes by French chemist Charles Adolphe Wurtz. These first reactions between an isocyanate and a hydroxyl compound would form the basis for the synthetic foam development boom that would occur almost a century later. The beginning of the 20th century would also see the emergence of other new synthetic polymers that would soon become the foundation for a new class of foams known as polymeric foams. The first successful polymeric foam product was based on polystyrene, a resin that was first synthesized in 1839 by Edward Simon. Initially called styrol, Simon did not realize the potential of his discovery as the substance was more of a thick, oily product than a usable plastic. Over the decades, more efficient techniques for synthesizing polystyrene were developed. This would lead to Ray McIntyre and his team at Dow's Chemical Physics Lab developing a method to produce foamed polystyrene in the 1940s, building upon a technique originally discovered by Swedish inventor Carl Georg Munters. Dow secured an exclusive US license for Munters' patent, and by 1947 filed a patent of their own enhanced method to mass-produce moisture-resistant extruded polystyrene foam branded Styrofoam. It should be noted that the trademark Styrofoam by Dow Chemical Company is informally used in the US for all foamed polystyrene products, although it technically only applies to extruded, closed-celled polystyrene foams made by Dow Chemicals. Extruded polystyrene, or XPS production, starts by mixing polystyrene pellets with additives, including colorants and flame retardants. This mixture is heated in an extruder until it melts. As this molten mixture is pushed through a shaping tool, a blowing agent within it vaporizes, causing the material to expand into a foam. Once it exits, it cools down, solidifying with a smooth surface. The solid foam is then trimmed to the desired size and, if necessary, given additional treatments for specific applications. Another common form of polystyrene foam is known as expanded polystyrene, or EPS. EPS production starts with raw polystyrene beads that are mixed with a blowing agent, usually pentane. In a pre-expander machine, steam is introduced, causing the beads to swell up to 40 times their original size as the pentane inside them heats up and expands. After this initial expansion, the beads are set aside in large bins for several hours to days, allowing the pentane to distribute evenly, a process called maturation. Once mature, these beads are placed into specific molds and steam is applied again, making them expand further and bond together to take the shape of the mold. The resultant structure is cooled, solidifying the foam. After cooling, the foam is precisely cut or shaped based on its intended purpose. Polystyrene foams are 95 to 98% air by composition and are ideal for building insulation use, packaging, and food containers. They are, however, not waterproof due to the interstitial gaps between the expanded closed-cell pellets in which moisture can become trapped. Extruded polystyrene typically has higher compressive strength and a lower moisture absorption rate than expanded polystyrene. As a result, it offers better long-term insulation performance when exposed to moisture. Expanded polystyrene generally has better insulative properties, though this can be decreased slightly with moisture absorption. However, expanded polystyrene is often more cost-effective than extruded polystyrene and can be custom molded into various shapes and sizes for specific applications. In 1937, German chemist Friedrich Baer would expand upon the discoveries of Charles Adolphe Wurtz with the development of the earliest prototype of polyurethane fibers known as Perlon-U. By 1940, the first polyurethane elastomers would be successfully developed. This class of polyurethane materials, whose physical characteristics are similar to that of rubber, quickly became a cheaper alternative to rubber during World War II, at the time when natural rubber was becoming rare and expensive. From this, World War II also saw the first attempts to create polyurethane elastomer-based foams, though this proved to be difficult due to the highly exothermic nature of the urethane reaction and quality issues. This sparked extensive research and development, especially in the United States, Germany, and Britain. Alternative hydroxy compounds were experimented with, and the process staged to manage heat. By 1954, the first commercial production of polyurethane foam based on polyester began in Europe and soon expanded to the United States. In 1956, DuPont introduced a new kind of foam material based on polyether polyols, which outperformed the existing polyester-based foams. These modern foams were easier and more efficient to produce on a large scale. Their superior physical properties also made them more popular. By 1957, the introduction of silicone surfactants in foam production would allow for smoother, more stabilized foams, making them more versatile in its applications and leading to a surge in its popularity. To manufacture polyurethane foam, two components are required: polyols and isocyanates. Both of these components are liquids that, when mixed, react to form a solid. Before the reaction to form the foam begins, a blowing agent is introduced. Initially, chlorofluorocarbons were used, but due to environmental concerns, they've been replaced with more eco-friendly options like water or hydrofluorocarbons. When the blowing agent is heated, it turns to gas, creating the foam's bubbles. Additionally, catalysts, flame retardants, and surfactants can be added to achieve specific foam properties. Once the components are mixed, the reaction starts quickly, producing carbon dioxide gas. This causes the mixture to expand or rise. As the foam rises, it begins to set. The entire process can happen within minutes depending on the formulation and the desired foam properties. Once cured, large blocks of polyurethane foam are often cut into desired shapes and sizes using special saws or hot wire. Depending on its intended use, the foam might undergo additional treatments. For example, memory foam, a type of polyurethane foam, undergoes additional chemical treatments to give it viscoelastic properties. Similarly, a foam for specific use might be treated for added flame resistance or antimicrobial properties. With modifications to the constituent chemical ratios and additives, a variant known as rigid polyurethane foam can also be produced. Rigid polyurethane foams are effective insulators due to its low thermal conductivity and boasts a low density, making it lightweight compared to metals. Additionally, it maintains its shape well, even under temperature changes, unlike metals which expand with heat. Its strong yet lightweight structure lends itself well for use in vehicles, aircraft, and building structures. Memory foam is another polyurethane-based foam with unique properties. Developed in 1966 by NASA's Ames Research Center, it's created by aerating a proprietary additive blend by introducing gases. This process creates the open cell structure that makes memory foam breathable and allows it to temporarily retain the shape of an object pressing into it. In the 1960s, around 100 companies produced foam in the United States, leading to the creation of foam plants nationwide to reduce shipping costs. By the 1970s, the foam industry witnessed significant changes. First, the number of producers shrunk from 100 to approximately 20 due to industry consolidation. Later, concerns about foam's flammability prompted the establishment of an industry association to address fire safety. By April 1980, the association officially formed as the Polyurethane Foam Association. During the 1980s, the polymeric foam industry grew dramatically as new technologies such as injection molding, twin screw, and several other extrusion and molding techniques were developed. One example of this are self-skinning foams, a type of foam with high-density skin and a low-density core that are formed through molding. New polymeric products began to appear on the market, offering a wider range of material properties. Ethylene vinyl acetate, or EVA, low-density polyethylene, or LDPE, and polyvinyl chloride, or PVC foams began to appear on the market in a wide range of packaging, insulating, and cushioning products. While synthetic rubber foams made from nitrile, neoprene, and silicone foam would be developed for sealing products, heat-applied elastomeric membranes, and specialty clothing and protective gear. Around this time, concerns began to grow over the emissions created by foam products, particularly long-exposure products such as mattresses. Because most polymeric foams are combustible, newly adopted regulations had required them to be flame-resistant. Historically, the fire retardant polybrominated diphenyl ethers, or PBDE, was used in these products. Additionally, methylene chloride, an ingredient in foam production, had been highlighted by the U.S. Environmental Protection Agency to cause central nervous system effects like headaches and memory loss. Sustainability also became an issue. The post-consumer fate of polymeric foam is highly dependent on the product that contains it. For example, a significant amount of furniture and mattresses are still being landfilled or incinerated. Many polymeric foams cannot just be melted at the end of its useful life to make new products. A massive effort by both the US and EU is currently being undertaken to make polymeric foams more sustainable. This includes constant research into new raw materials as well as the development of recycling technologies and infrastructure to allow recycling of polyurethanes to be done at its full potential. Beyond traditional polymeric foam products, various exotic foam compositions have been explored over the decades for extreme environment use. Syntactic foams, or composite materials synthesized by filling a metal, polymer, cementitious, or ceramic matrix with hollow spheres called microballoons have been used in both aviation and deep-sea exploration. Metal foams, such as aluminum foam, have even been explored for use in blast and ballistics protection. Nanofoams, a class of nanostructured foams containing pores with diameters less than 100 nanometers, such as aerogels, are currently in active development. Foam has undergone incredible advancements throughout its history. With its superior properties, it has become so integral to numerous everyday items that it's difficult to envision our daily lives without the benefits of foam. While producing a foam is a relatively simple, natural process, creating engineered foam products with specific physical properties and in large amounts require a careful degree of process control. The industrial control systems that drive the modern foam industry relies on specialized software that guides the entire process. Have you ever wanted to build an understanding of coding and explore how it is applied to manufacturing? Well, there's a free and easy way to get started immediately. That's where Brilliant.org comes in. Brilliant.org is my go-to tool for diving headfirst into learning a new concept. It's a website and app built off the principle of active problem solving. Because to truly learn something, it takes more than just watching it. You have to experience it. Brilliant is constantly developing their courses to offer the most visual, hands-on approach possible to make mastering the key concepts behind today's technology effective and engaging. One course I strongly recommend is Brilliant's Thinking in Code. This intuitive progression of visual computational problem solving lessons help you develop an understanding of how code works and its connection to real-world applications using interactive exercises that intuitively connect the conceptual to the real world. With Brilliant, you learn in depth and at your own pace. It's not about memorizing or regurgitating facts. You simply pick a course you're interested in and get started. If you feel stuck or made a mistake, an explanation is always available to help you through the learning process. To try everything Brilliant has to offer free for a full 30 days and start learning STEM today, visit brilliant.org/newmind or click on the link in the description below. The first 200 of you will get 20% off Brilliant's annual premium subscription.